everyone. Today we will present about flow measurement. So for this experiment, I am the leader. My name is Siti Nur Antasha binti Suhaimi, and my group members is Raven, Nurul Nafisha, and Pavitra. Okay, so this is the content that we will present. Next. Okay, so summary for this experiment is, with the application of Bernoulli's theory, the relationship between flow and pressure can be determined. It was found that when the flow rate increases, the velocity will increases and the pressure will decrease. From the data analyzed, we can compare that in different equipment, the flow rate will be different, and we have venturimeter as the most accurate measurement because the discharge coefficient is applicable and less but closer to 1. The objective of the experiment is to determine the relationship between flow and pressure through different flow meters and to investigate the corresponding discharge coefficient for each flow meters by applying Bernoulli's equation. Fluid flow can be categorized in a few ways depending on the various characteristics of the flow. A flow meter is used to calculate the flow rate of the fluid or energy to allow the process to be monitored and to ensure that the final product is of the required quality. And then the result for the difference between H1 and H2 is recorded for all three equipment, which is orifice plate, nozzle, and venturimeter. The average discharge coefficient values are 0.4461, 1.1088, and 0.9393, respectively for orifice plate, nozzle, and venturimeter. In this experiment, when the velocity of the fluid is rises gradually, we can see that the pressure of the fluid will be decreased. Measuring the flow rate is an important aspect in our industries, and there are several ways to measure the flow of fluids in pipes. The measurement of fluid flow is important in applications ranging from measurement of blood flow rates in a human artery to the measurement of liquid oxygen in a rocket. Okay, next. Oh,
So
wait,
next,
so next, Raven will present about the theory of the experiment.
thank you, Natasha. So I'm Raden. I'm going to present about theory. So in this experiment, we used a few types of measuring devices to determine the flow rate of fluid. The devices that we used are an orifice plate, a nozzle, a venturimeter. As we all know that the flow rate calculation is the cornerstone in manufacturing considerations. This is because its importance has many effects on variables such as pressure and temperature. Therefore, to ensure the efficiency in the function of the system, it is important to select the appropriate flow meters. So first we look into the orifice plate. Orifice plates are one of the most common devices for measuring and regulating flow of fluid. An orifice plate is a restriction with an opening smaller than the pipe diameter which is inserted in the pipe. It is used as limiting devices to regulate fluid flow or to minimize the flow pressure downstream of the orifice plate. Orifice plates are often tightly coupled to a gate valve. Usually, the orifice plate is a constraint with an opening smaller than the pipe diameter that is inserted into the pipe. The velocity of fluid would increase and hence reduce the pressure due to the smaller opening area. By using this orifice plate, we are able to assess the flow rate from the measured drop in pressure which is P1 minus P2. The orifice plate is most common used flow sensor in the industry. However, due to the turbulence around the plate, it creates a very high non-recoverable pressure and resulting in high energy consumption. So this figure 4.1 shows a schematic representation of orifice plate meter. So this is the equations. QTH, which is Q theoretical flow rate, is equals to A2, which is cross-sectional area of orifice plate, times with the square root of 2 times P1 minus P2. P1 minus P2 is a differential pressure between points 1 and 2 over density bracket 1 minus A2 over A1 square. Thus, Q theoretical is equal to A2 square root 2 P1 minus P2 over density bracket 1 minus A2 over A1 square. And the coefficient of discharge QD is equals to Q actual over Q theoretical. So next we look into the nozzle. Nozzle is a method of measurement that is known in which the fluid flow velocity increases the pressure. The nozzle meter is a modification of the Venturi tube, allowing the fluid to interact with the opening of the nozzle with an oval restriction and its throat to decrease the pressure before the lowest cross-section region is extended. At the point of the nozzle, the lowest pressure must proceed until it reaches the nozzle. Even though the nozzle attachment is easier than the Venturi meter, however, it is much difficult than the orifice plate. The nozzle was controlled by the same laws and equation as we saw just now, which is the orifice plate in 4.1, with only changes to the cross sectional of nozzle. As in the figure below, the difference between them can be determined by the shape of the small opening, the nozzle being around a quarter ellipse. Next, this is the Venturi meter. Venturi meter is a well-known flow measurement apparatus. It was designed based on the principle of Bernoulli's equation and used to measure the flow rate liquid through the pipes. By reducing the area of the passage, pressure in the pipe will be affected. With the help of manometer, the flow rate of the liquid can be determined due to the pressures difference. Venturimeter consists converging section, diverging section, and throat diameter. The velocity of flowing water will increase when water passes through a smaller cross-sectional area of pipe, which is the converging section. Thus, the pressure will also decrease. The velocity and pressure of the flowing fluid will remain constant when passes through the throat diameter as the area is remained as constant, which is shown in the figure 4.3, the schematic representation of venturimeter. However, in the diverging section, the cross-sectional area is increasing from small to big. The increase in area will cause the velocity of flowing water and pressure reduce. Next, I will leave it to Antasha again.
Okay, so for this experiment, this is all the apparatus that we use. The first one is multi-tube manometer, orifice plate, nozzle, water inlet, venturi, main switch box, flow control valve, sump tank, gate valve, water outlet, rotameter, and ventilation valves. Okay, next. So the procedures are, okay, the first step is the orifice plate was ensured being properly fixed at its position and the manometer tubes, which is H1 and H2, were fastened to the orifice plate. Next, the flow control and the gate valve were closed and the main switch and the pump were turned on. The third step, the flow control and the gate valve were opened slowly and simultaneously until their maximum opening level, which is the water in the manometer overflowed was reached. Next, to release all the bubbles in the system, the ventilation valve, which is the black one, was opened by turning it to an anti-clockwise direction. Then, the ventilation valve, which is the black one, and the gate valve were closed, and then the pump was turned off. Okay, next, the ventilation valve, which is the white one, was slowly opened until the minimum water level of 30-40 millimeter was reached. Then the pump was turned on. Okay, next, the gate valve was opened slowly until the level of water in H1 reached maximum 390 millimeter and the manometer H2 was at its minimum level. All the readings which H1, H2, and Q at were being recorded. Next, the gate valve was closed and the pump was being turned off. The manometer tube, which is H1 and H2, were removed from the orifice plate. Okay, next, the orifice plate was replaced with nozzle, and steps 1 to 7 were repeated. Meanwhile, for the venturi, the manometer tubes were connected to H1 to H3, and the similar steps to step 1 and the similar step, which is from the steps 1 until step 7 were applied. And then the last one, after finish, the manometer tubes from the system were removed. The flow control valve was also closed and the pump and the main switch were being turned off. Okay, next. Okay, Pavitra will explain. Nafisha will explain about the data of the experiment.
I am Nafisha and I'm going to continue with the data of this experiment and also the results obtained from this experiment. So these two tables shows the data for orifice plate and also the nozzle. Firstly, we are given the value of Q rotameter, which is the actual flow rate of water in liter per hour. The value of Q rotameter should be around 200 liter per hour and above in conducting this experiment. We are also given the volume of water collected, which is 3 liters for each reading of Q rotameter. Then we have the time taken of the flow of water in unit seconds, the value of H1 and H2, which is the height of manometer at point 1 and point 2, the value of inlet pipe diameter and outlet diameter, in which we can obtain the area to calculate the Q theoretical. Next. So this is the data for the venturimeter. For the same like the previous slide. So next. Next slide. So this is the results obtained from the experiment. Q actual can be calculated using formula of volume of water collected, which is 3 liters, divided by the time taken of water flow obtained from the experiment. Then Q theoretical can be calculated using Bernoulli's equation, which is A2, the outlet diameter times with the square root of 2G, G is the gravity constant, times with the differential in height manometer, H1 minus H2, divided by 1 minus A2 over A1 squared. So by obtaining the values of Q theoretical and Q actual, we can calculate the value of discharge coefficient of each flow meters. CD values is calculated using formula Q actual divided by Q theoretical. Next. Next slide. So this is the result obtained for venturimeter. So this is the example of calculation to obtain the discharge coefficient. Firstly, we need to calculate the area of inlet and outlet diameter of each flow meters, which is the orifice plate, nozzle, and venturimeter. So then we can calculate the Q theoretical using the equation that I have mentioned just now. Then lastly, we can calculate the discharge coefficient. These calculations are repeated for each flow meters with each values of Q rotameter so that we can compare the discharge coefficient between the three types of flow meters. So that's all from me. I will pass to Pavitra to continue our presentation.
So for the discussion, there will be 3 parts we'll discuss. Firstly, the difference on water level in manometer with different types of flow meters, which relates with pressure losses associated with types of flow meter. This case can be explained by applying the Bernoulli equation. The concept of Bernoulli, formulated by Daniel Bernoulli, stated that the pressure within the fluid decreases as the speed of moving fluid increases. Therefore, due to the condition of flow meters, the H1 and H2 values of the orifice plate, nozzle, and venturimeter differ. Water level differences in the manometer vary with the type of flow meters. There are graphs plotted to determine the pattern of H1 and H2 and the difference in H. According to all 3 graphs, it is clearly shown that H1, which is maximum water level, is always higher than H2, which is minimum water level. The orifice plate is constrained with an opening smaller than the pipe diameter that is inserted into the pipe. The region for the opening is smaller. At H1, the height of the water level is higher because the pressure in the fluid was produced to flow through the smaller opening area. As consequences of this condition, the fluid velocity increases and the pressure decreases at H2 and lessens the height of the water surface. When using nozzle, the height of H1 increases as the volumetric flow rate increases, while the height of H2 decreases. This is because a nozzle with an opening has a limit. This opening of the restriction causes a frictional force to occur in the tube. As the fluid increases, the nozzle acceleration, the velocity increases, thus reducing the strain, allowing a relatively large difference in height. Thus, the decrease in pressure causes the H2 reading to drop. Next, in venturimeter, the H1, the value of the water level is greater than H2. This happens because the venturimeter consists of a segment that converges rapidly. While the velocity is lower, it makes the pressure at H1 greater. But the pressure continues to decrease as the fluid moves through the H2, while the velocity of it increases to lower the water level at H2. Next slide. Next, we would like to discuss the difference in discharge coefficient, CD, value for each of following flow meter and the ranking of the flow meter according to their accuracy. The value of the discharge coefficient is necessary because the accuracy and efficiency of a flow meter is established by it. Based on the table and graph log difference in H against actual flow rate actual flow rate measured from experiment, each flow meter has a different average discharge coefficient value. This is because the Q actual and Q theory ratios are the CD. The smaller the difference between a flow meter's Q actual and Q theory, the greater the coefficient discharge, the greater the accuracy. When a liquid flows through a flow meter, the distinction between Q actual and Q theory is strongly dependent on the loss of head and friction. The Q actual will decrease for a flow meter causing greater head loss and loss friction. Therefore, the accuracy of the flow meter decreases when the difference between Q actual and Q theory becomes greater and the discharge coefficient becomes lower. From the result attained in table, nozzle has the highest discharge coefficient of 1.05424, while orifice plate has lowest, which is 0.399056. However, the coefficient discharge can be never be greater than 1. The flow meters are made up of different kinds of shape, and Venturi meter, geometrically shaped, has causes it to have a small friction than the other two flow meters. So the CD for Venturi is the nearest to 1. So the ranking flow meters according their accuracy is Venturi meter, nozzle, and followed by the orifice plate at the least precise meter. Next slide. And finally, factors contributing to errors and inaccuracy in this experimental data and possible recommendation to improve the existing result is, in the experiment result, there were a few inaccuracy or errors due to a few variables. First and foremost, the observer's eyes are not aligned with the pointer and scale when reading the rotameter and multi-tube manometer. This causes parallax error to occur. Secondly, there are air bubbles trapped inside the system when conducting the experiment, and a short time is given for the ventilation valve to be opened so the air bubbles did not have enough time to escape. Then, the experiment for each flow meters are only conducted one for each value. Finally, lack of proper connection between the tubes and the manometer causing the water leakage to occur. If there are errors happen in the experiment, for sure there are always modifications that can be made through, so that these mistakes can help to a minimum. Firstly, the observer's eye should be directly perpendicular to the pointer and scale when reading is taken to avoid parallax error. Next, allow sufficient amount of time for all bubbles trapped to escape in the system. Thirdly, the experiment should be repeated at least twice for each flow meters. This is to ensure that we get an average reading of rotameter and multi-tube manometer. In addition, lab manual should be read by students before entering the lab and conducting the experiment. Next, I would like to pass to Antasha.
Conclusion, in general, we all know that flow rate is defined to be the volume of fluid or gas passing by some location through an area during a period of time. So in this experiment, flow rate was measured by using three types of flow meters, which are orifice plate, nozzle, and venturi. So the operation are determined by comparing pressure drop and related to the velocity of the fluid in the pipe using Bernoulli equation. The same physical principle is used, which is an increased velocity results in a decrease in pressure. So, based on the results, Ventrimeter is the most accurate flow meter because the CD value is approximately to 1, which is 0.9393. Okay, so as for the nozzle, CD value is 1.1088, followed by orifice split, which is the least accurate flow meter, as its CD value is the lowest, which is 0.4461. So, this is due to the much energy being lost as it flows and causes a pressure drop in the fluid. Okay, so that's all from us. Thank you.